Hello and welcome to the Cornish Radio Amateur Club series of instructional videos for the UK Radio Amateur Examinations. I'm Rick Hall, G4PGD, and today we're going to tackle syllabus item 2C3, which we've called PD and EMF. This topic isn't tested at foundation level, so starting at intermediate license level, the difference between EMF and PD is often a cause of confusion, but it's worth sorting it out as it has implications for the amateur designer and builder, and even if you're connecting a power supply to a radio. One way to think of the difference between EMF and PD is as cause and effect. Consider a simple circuit with a cell and a resistor. The cell has an EMF which causes a current to flow, and the effect is a potential difference across the resistor. The graphic shows a stylized battery made up of 4 cells with a resistor Rint representing the internal resistance of the battery. In reality, the internal resistance depends on the type of cell and is due to effects like sulfaction and grid corrosion in lead-acid cells and crystalline formation in nickel-based cells. These chemical mechanisms are beyond the scope of the intermediate course, and it's sufficient to know that there is internal resistance and convenient to represent it as a single imaginary resistor. Although, of course, it's distributed within the cells. In the case of alkaline batteries, a new AA cell will have an internal resistance of about 300 milliohms. So 4 cells in series will have a combined internal resistance of about 1.2 ohms, and that's what Rint is representing. If SW1 is open, there is no current flow in the circuit, and hence there is no voltage drop across Rint. The terminal potential difference will be the same as the EMF, i.e. 6 volts. But if SW1 is closed, the current will be I equals EMF divided by Rint plus R load, which equals 6 divided by 1.2 plus 10, and that equals 536 milliamps. And the voltage dropped across Rint will be Vrint equals I times Rint, which equals 536 times 10 to the minus 3 times 1.2, and is approximately equal to 643 millivolts. So when the switch is closed and current flows, the voltage across the load, R load, will be correspondingly reduced. We can work this out in 2 ways. Either using Kirchhoff's voltage law, VR load equals EMF minus Vrint, which equals 6 minus 643 times 10 to the minus 3, or approximately equal to 5.36 volts. Or using Ohm's law, VR load equals I times R load, which equals 536 times 10 to the minus 3 times 10. The same answer again, approximately equal to 5.36 volts. This example has used typical values for alkaline cells, which, although they have quite high capacity, also have quite high internal resistance and are therefore not well suited to delivering high currents. Lead-acid cells have much lower internal resistance and are better suited for applications such as vehicle batteries which need to be able to deliver high currents to crank an engine. The internal resistance of a battery is illustrative of the more general concept of source impedance that extends to such devices, AC devices, as signal generators and transmitters, which is explored in greater detail at full license level in syllabus item 9A4. The maximum power transfer theorem. Full licensees or full license candidates only. This is not required learning at intermediate level, but helps to give us context for syllabus item 9A4 later on. Let's start by replacing the picture representation used in the graphic with a schematic. If we vary the value of RL from 0 ohms to 1.8 ohms in steps of 0.2 ohms, we can calculate the current and hence the power, PRL, using Ohm's law and power formulas. So we can calculate the power in the load when the current is a short circuit, 0 ohm, when the load is 0.2 ohms, 0.4 ohms, 0.6 ohms, etc. Putting the results into a table and graph demonstrate that maximum power is developed in the load, RL, when the load resistance is equal to 1.2 ohms. That is, when RL equals RS, or putting it another way, when the load resistance equals the source resistance. The maximum power transfer theorem has implications for connecting an amplifier to a load. Maximum power will be transferred from the amplifier to the load if the amplifier source impedance equals the load impedance. This applies to an audio amplifier connected to a speaker or an RF amplifier connected to an antenna. These are the points to remember. EMF is cause and PD is effect. EMF sources like batteries and signal generators have resistance or impedances for AC sources like oscillators. The voltage drop within the source device due to the current flow results in a reduced terminal PD. And a bit of extra learning, appreciate the implications of the maximum power transfer theorem. The next short video, 2C4, addresses polarity at foundation level. The syllabus simply states that the polarity must be correct for electronic circuits to function correctly or damage may be caused. If this is self-evident to you, you may wish to skip 2C4 and move on to 2D1, which starts at intermediate level and looks at capacitors and dielectrics. Or, if you are sticking to foundation studies, then the next syllabus item for you is 2E1, DC and AC. So that concludes syllabus item 2C3, PD and EMF. Thank you for watching.